in this demonstration, we're going to talk about the conductivity of solutions. And really the concept that we're trying to explore here is what solutions actually have the movement of ions or allows for the movement of ions in that solution. So we're going to explore about 6 different solutions here to see which ones are conductive or not, and just kind of get you a feel for conductivity. So we're just going to start with normal DI water here. Again, not really any ions here. It's actually filtered out water so it can just maintain its pure H2O status per se. So let's go ahead here, and we're going to put this water into this conductive meter here. So on the top, what you should see in the camera here is a meter that can essentially let you know if the solution is conductive or not. On the left side, if that arrow starts to spike up, then you know the solution is conductive. And as we see here with the DI water, there's really no movement in that meter, so we know it's not a conductive solution, which makes sense. There's really no ions present in DI water, which filters out those ions. Now, when we go with normal tap water here, which can essentially come from a lot of different sources, maybe there might be ions that come from the minerals in the rocks that can allow the tap water to maybe have some conductivity. So let's go ahead and run this here, and we're going to just give a little bit of up and down motion of this, and you should hopefully see the meter in the arrow in this meter start to just kind of really spike up a little bit. So not really conductive, but more than DI water per se, which is completely a non-conductive material. All right, now we can start talking about a different solution called methanol. So methanol is very polar. But what's unique about methanol is the fact that when you actually dissolve it in water, it does not ionize, it does not dissociate into different ions, and maintains itself as a molecule. So because of that, it does not have any sort of ability to generate movement of ions. So if we now take this methanol solution here and we place it inside of this conductive meter, as you can see in the meter as we have the solution there, that there's no movement of the arrow. So we can see again that this solution is not very conductive. So what we would call that solution is a non-electrolyte solution. So again, non-electrolyte means that it's not conductive. All right, now let's move on to the next one. We have here what we call HCl, hydrogen, help me out here.
Hydrochloric acid.
Hydrochloric acid. I don't know what's going on with my brain today. I don't know, something's giving me a brain error. But we have hydrochloric acid here. So hydrochloric acid is a really strong acid, completely dissociates into water, generating both positive and negative ions. So when we take this hydrochloric acid and we dilute it, of course this is a diluted solution here, so we can still place that into this conductive meter, and as we place it in the conductive meter, we now can see that it's really generating a lot of conductivity in this. It's demonstrating that the solution is conductive. So we can see here the arrow has spiked up. All right. Thanks for my not my sous chef, but maybe call him my sous chemist, right? So thank you for the help in clarifying that. Perfect. Let's continue on. Acidic acid. Now, acidic acid is not a strong acid. It's a weak acid, but nonetheless, it still dissociates some ions into the solution. So we can suspect, and hopefully you guys can predict this, that if it does dissociate ions into the solution, it should have some type of conductivity. Maybe not as strong as HCl, but we should see something. So as I place this in the conductive or the meter, we can start to see a little bit. If I move the solution up and down out of the meter and into the meter, you see the arrow kind of go back and forth, but really similar to the tap water, it's really not that conductive. All right, let's move on to our last 2 solutions that we're going to create for this demonstration. We have just typical table salt that you use at home, sodium chloride. And when we mix that in some water, what now actually happens is similar to the HCl that we have here, it actually dissolves and completely dissociates into ions in the solution. A little fun fact here is that this is really not a strong acid like the HCl, but it's still the fact that it dissociates completely into the water will give you a nice conductive reading. So as I place this into the meter, you should see the arrow spike up indicating that this in fact is a conductive solution. Again, conductive solutions, we call those electrolytes. Non-conductive solutions, we call those non-electrolytes. Now you have the fun job here of guessing our last solution that we're going to create, which is just normal table sugar in water. So if I told you that table sugar, when it dissolves in water, is very similar to our methanol, where it does not actually dissociate into ions when you place it in water, I want you to predict whether or not it will be conductive. Again, when we take that table sugar, the molecules of the table sugar, it dissolves in water, it does not dissociate into ions. So as I place it in here, into the conductive, or into the meter, we can see that in fact, it is non-conductive. It's a non-electrolyte solution because it does not generate any movement of ions. All right, so hopefully that helps you understand a little bit about how you can predict whether solutions are going to be conductive and what type of solutions are conductive. Thank you.